Beautiful. Hey everyone, my name is Hugo. I'm a graduate student at UT Austin in Tom Yankilov's lab. And today I will tell you about a patient shows up at the hospital and diagnosed with breast cancer. And so the doctors are going to come up with a whole treatment plan with chemotherapy and radiotherapy and surgery and all of that. And you're going to image your patient along the way. And then after months, weeks of therapy, then maybe if you're unlucky, not only do you still have cancer, but maybe you possibly have even more cancer that you had before, simply because your treatment just failed. And so why is this happening? Why do treatments fail? Well, there could be many reasons, obviously, but one of them that I believe we're all familiar with is tumor heterogeneity, right? Right. So we know that solid tumors are composed of a whole diversity of cell subpopulations, each with their own genetic signatures and potential to react to treatment or not. And so this heterogeneity is found within a single tumor, but also in between two tumors within the same patient, and also obviously between two patients. And so that's an issue, and we're going to try and address this by designing an experimental computational pipeline to first model and characterize the response to treatment of tumors through the prism, through the lens of heterogeneity at the in vitro scale. And so how are we going to do this? So first, what we've done is that with cultured cells in dishes. And so we let them grow for 48 hours, and then you hit them with a chemotherapy. So doxorubicin, you'll just standard of care breast cancer chemotherapy. And then you image them, take pictures every 4 hours for weeks, and you just look at what happens. And so we tested 9 different concentrations with 6 replicates per concentrations. And we take those beautiful pictures, which we can load into MATLAB or anything else, and we can turn them into those cell density maps. Once we have those, we're going to come up with some model to describe the evolution of the cell course and the spatial dynamics. So I'll go over the model in just a second. Once we have the model, we take the cell density maps, and we can calibrate the model onto the maps. And so the model that we have is a PDE-based model because we have obviously a temporal component, but obviously a spatial component, because that's what we're trying to catch. We're trying to catch the spatial distribution of the cells. Once all of this is done, once the model is calibrated nicely, we're going to try and make predictions. And so how are we going to do this? So we figured out that trying to predict the whole time course starting from the treatment was just too challenging. So instead, we're going to try and make predictions on weekly segments. So if I'm at time t, I want to be able to tell you what your tumor is going to look like at time t plus 1 week. And so we're going to use a data assimilation pipeline, as we call it. And so the general idea is to say, so as I told you, we have 6 replicates per concentration. So I'm going to take one of them and leave it out, just isolate it, and I'm going to try to make a prediction onto this guy. And I'm going to do this by making a training set out of the 5 replicates that I left out. And so by calibrating my model on those 5 replicates that I left out, I can make a first prediction on this one guy that I isolated and that I want to make a prediction on. So I can make a first prediction for the first week. And when that's done, then I can go and I can measure my cells, like take pictures of my cells, measure my cell count on this one replicate, and I can compare the two, compare my prediction and my data that I measure. And now that I have access to this data right here, well, I can include this data as well into my calibration framework to have some idea of what the parameters on this guy are going to be. And now using this, I can make a new prediction for the following week, again like this. And then measure again and compare the two. And as time goes on and we assimilate more and more of the data into the calibration framework, well, hopefully the predictions will get better and better. And when this is done, we can make predictions, not only predictions of the cell count. So I will be able to tell you how many cells I have in my dish, but also, and arguably most importantly, where they're going to be. Okay, terrific. So let's go over the model. So at first, as I told you, we let the cells grow for 48 hours. And during this phase, we consider that the population is just homogeneous. And we can model this through your usual exponential growth, nothing too fancy. So again, PD model, space, time, diffusion, all of that. Then boom, you give the treatment. And then you enter the post-treatment phase. And in this phase, we're going to consider that we have a surviving phenotype. You could also call this resistant, which again, basically goes and is unaffected by the treatment. And so this will also follow classic logistic growth. And then you have the damaged or sensitive phenotype. And those cells, they're still going to grow for a little time, just to give like the drugs the time to get inside of the cells and do its thing and disrupt the DNA and all of that. And then those cells are just going to decay and die off. And if you sum up the two, you have the total population. Okay, terrific. So let's take a look at some of those pictures. So again, we see the cells, wait 48 hours, give the chemo, and then we measure. So if you give just 10 nanomolar, so basically just a little droplet as a treat, your cells are going to grow and you're going to get your nice little logistic growth, and you don't see any kind of spatial heterogeneity. Your cells just fill the dish and you hit carrying capacity and everything is all nice and well. If you give 300 nanomolar, which is a lot, again, you don't really see anything interesting because all your cells are just dying. You don't see any patterns of spatial distribution. But if you give something in the middle, like 100 nanomolar, then what do we have? Okay, so the cells just die off. And after a couple of weeks, we start seeing those clusters of highly proliferating cells popping up here and there, and you end up with this completely heterogeneous structure. And this is really what we're going to try and model and hopefully predict. So now we can take those cell counts, like time courses over there, and those cell density maps that I told you about a second ago, and the model, and we can calibrate all of that. And this is basically what you get. So 9 concentrations from 10 nanomolar to 300. I'm showing you 1 representative replicates per concentration. And as you can see, the model is fitting just fine, no issue here. And so we can blow up one of those guys from the 100 nanomolar data set. So this is my bulk calibration. So by bulk, I mean like the total cell count, like just total cell count in the entire dish. You can see the model calibration right here. This is all nice. And then those are the cells at the final time point. So T equals 800 hours. So I can take this and I can superimpose my cell density map. All right. And this is what we calibrate the model on. And so for instance, I can blow up this area right here and we can take a look at this pixel here. So you can see the cell count, and I can't, maybe you can't see real well, but you can see the model being calibrated here as well. And I can show this pixel as well, which has a very different dynamics. And yet the model is able to fit nicely onto those 2 time courses here. If I show you this one last guy here, so this one is kind of strange. If you look at the movie, so the cells are kind of dying off for like 300 something hours. And then we have some cell infiltration from a neighboring pixel. And then those cells, they get in and then they don't move and don't do anything. So this is why you have this kind of plateau at the end. And this kind of outlier dynamics, the model cannot catch so well. But generally, we're doing a good job here. Okay, so this is the whole calibration step. This is the easy part. Now we move on to the predictions. So again, So how do we do this? We let the cells grow 48 hours. And I take my training set and I will make a first prediction for a week. So this is my prediction. This is where I think my cell count is going to go. So then I'm going to measure, like go to my microscope and measure where my cells are and count them. And this is what I get. This is my measurement. Cool. So now I take this measurement, I assimilate it into my calibration framework, and I can make a new prediction for the following week. And then again, I measure. Again, I assimilate, I make a new prediction, and I measure again. And you get the idea, and hopefully at the end, we get a nice prediction that lines up decently. And if I show you this over the whole data set, this is what we have. So those are predictions made on all of those different concentrations. Again, overall, we're doing a nice job. Some funky things happening here and there, like on the 35 nanomolar. But overall, it's working pretty decently. So again, let's blow up this 100 nanomolar guy. And so now we'll take a look at the actual predictions of spatial distribution. So after the first week, this is what we have. So on the bottom row, you have the measurement, the data. And on the top row, you have the prediction that we make through our pipeline, through our model. So at this point, it's kind of too early to see anything happening. So let's move on. This is the second week. And maybe you can see on the bottom row, you have like one of those clusters, like on the bottom left of the picture, bottom right, sorry. But you cannot see it on the top row on the prediction. Why? Because this just appeared in the last week, but the last week was not yet included in the calibration framework. But then when we assimilate this week of measurement, now we can start seeing it on top, like on the bottom right. And then at this point, it's kind of smooth sailing, and then we can really predict the patterns of cell distribution pretty decently. So quick conclusion. So our model is able to characterize and capture the data really nicely. It can fit very well onto the data. We have a prediction pipeline to predict the major patterns of cell distribution. And all of this is part of the effort to bridge the gap between chemoresistance, resistance to treatment, and heterogeneity. And now the next step is to try and apply this whole prediction pipeline to in vivo data. So we have a bunch of glioblastoma data that we got from MD Anderson in Houston. And the goal would be to do exactly this, to basically try to predict how the tumor is going to evolve from one patient visit to the next, and hopefully try and adapt the therapy in consequence. So with all of that, I would like to thank you all and thank my team at UTRC, my PI, Tom, Ernesto, who's somewhere over here, and my trusty undergrad, Sophia. Thank you so much.
Hey, really nice work.
Thank you.
So I'm thinking this is very nice. You have everything in vitro, and I believe there will be probably people who are like, "Oh my God, yes, we can predict tumor heterogeneity in a petri dish."
Yes,
growing. It's a petri dish. So I could imagine that there will be potentially some criticism of people coming to you and saying, "Oh, but what if you bring it to the real tumor, where you have blood vessels, where you have, where you have adult cells competing for space, and a lot of other factors." And I'm wondering if because you're now going, it's a very huge step to go from petri dish to the glioblastoma patient set, which is a completely different type. And I'm wondering if you have any opportunity to do something in between, maybe like, do you maybe have access to some data that are, like, say, organoids, where when instead of not looking essentially at it's like kind of in between the whole in vitro and and clinical data, but maybe some mice models, maybe some organoids.
So, well, what's good with our team at UT is that we have kind of the whole pipeline from in vitro data to clinical in vivo data. And we also have a lot of preclinical mice data as well. So we could potentially use that probably. But also, I'm not jumping entirely into the GBM field just like that. Like I'm standing on the shoulders of giants already. Like we have been working with in vivo GBM data for a while. David over there has been doing this extensively over the years. So we already have models. We have been developing prediction pipelines in the past. And this is a new approach that we are suggesting. So for me personally, it's a huge jump because I've been mostly working with nice in vitro data so far. But so now jumping to GBM data is, as you said, quite a challenge. But we have the teams, we have the scientists, and yeah, and so we have all of those data already from MD Anderson, and it's pretty convenient for us because we have a nice, or at least based on my restricted experience, like the data that we have a nice temporal resolution in the sense that we have something like 9 to 12 time points per patient, which I believe is good. I mean, I've seen data sets with way fewer data points. So could we do something in between? Probably. At least for now, I'm going to try and stick with GBM, and we'll take this wherever we can. That's the idea.
Okay, cool. Sorry, just like continuing on that, because I think this is actually really interesting, because if we think about that, yes, we can always try to predict exactly how tumors will grow and respond, but there is also a challenge and I think a great opportunity to learn where it fails. What are the missing parts?
Right.
We've just been hearing so much about, we've been hearing so much about interactions in between different cells. And I think that is going to be probably the part of the challenge of going from the in vitro to the glioblastoma data set. So, so yeah, I think this is really interesting. And I think there's a lot of really fun things that are coming out from this work.
Yeah, absolutely.
Thank you.
Thank you.
Hi, thank you for your talk. So I had a question actually about the mathematical model. So I think on the second to last slide, or the last slide that you showed the data assimilation, it looked like maybe the one before that where you were showing the step-by-step. This one. It looks like up until that last measurement, your model is pretty consistently underestimating the actual measurements. And just out of curiosity, was this something you saw in a variety of different measurements, or like were you thinking about when does this happen?
So across the entire data set, I have not seen a consistent underestimation of the prediction. Like sometimes you're going to overshoot, sometimes undershoot. I haven't seen anything systematic. So in this particular replicate,